Hello. So let us start the lecture. So in the previous lecture we discussed F sigma sets. So in this lecture we define oscillation of a function, a real valued function, over some interval, and then we define oscillation at a point, and finally we will see the relationship between the continuity at a point and oscillation at that point. So let's first define oscillation over interval. Definition. If f is a function from R to R, and J is any bounded interval, and J is any bounded interval of R, we define oscillation of F over J by, this is the notation for the oscillation of F over J, and the definition is it's equal to the least upper bound of F where x runs over J minus greatest lower bound of F where x runs over J. So clearly this is greater or equal to 0 because least upper bound is always greater or equal to the greatest lower bound. So this is called the oscillation of F over the interval G. You can easily find out the examples of oscillation. So you define any function from R to R and take any interval, you can easily find that least upper bound of F over that interval and the greatest lower bound of F over that interval. Then you will take the difference, that will give rise, that will give the definite, that will give you the oscillation of F over that interval. So let's now define oscillation of F at a point. Now if A belongs to R, if A belongs to, it's a real number, is a real number, we define oscillation of F at A by, that's the notation of oscillation of F at A, it's equal to the GLB, greatest lower bound of oscillation of F at a J, where this GLB runs over the intervals J, bounded intervals J containing bounded open interval. Okay, so in the definition this is bounded open interval. Okay, here, so where J runs over all the bounded open intervals, bounded open intervals containing A. Okay, so you fix a point, a real number, then you take the interval, bounded open interval J containing A, and you find the oscillation of F over that interval. And now you find all the intervals which contains a point A, and you find all the oscillations over those intervals, and finally you will choose the greatest lower bound, the least value among those. That's the oscillation of F at the point A. So since this is greater or equal to 0, so clearly this is clearly, so since this oscillation of F over J is greater or equal to 0, so its GLB is also greater or equal to 0. So clearly oscillation of F at A is always greater or equal to 0. So now when it's positive and when it's 0, so that's the next theorem actually, which give you the idea about this oscillation So this is very important because it connects with the continuity at a point. So let's state the theorem first here. Let f be a function from R to R and A belongs to R. Okay, then the following statements hold. Then the following statements hold. First one is, if this f is continuous at A, then oscillation of f at A must be equal to 0. And if it's not continuous at A, then oscillation is positive. Okay, if f is not, that means it's continuous at A if and only if oscillation is equal to 0. This is actually the theorem. If f is not continuous at A, if it's not continuous at A, then oscillation of f at A is positive. So assume that f is continuous. Assume that f is continuous at A. So it means that for each epsilon positive I can find a delta, or I can find a bounded open interval containing A such that any point x belongs to that bounded interval, so that the f of x must be in some interval having radius epsilon actually. So therefore for all epsilon positive, there now let's sit like this. Okay, let's choose any epsilon positive. Okay, let epsilon be any positive number. Since f is continuous, so then choose a bounded open interval, say I, containing A such that x belongs to I implies that mod of f of x minus f of A is less than delta, is less than epsilon. It's same as x minus A less than delta implies mod of fx minus mod of f of A less than epsilon, because if I write this x minus A less than delta, it's equivalent to write that x belongs to A minus delta A plus delta. So that's your interval I. So for every epsilon positive I can find an interval I such that whenever x is in this interval, f of x minus f of A is less than epsilon. Now we show that oscillation of f at point A is 0. So we have what's the oscillation of f at A? That's by definition it's the GLB of oscillation of f at J, where GLB runs over all bound open intervals containing A. So where GLB runs over all bounded open intervals containing A. So this implies oscillation of f at A, which here you see it's less or equal, it's the GLB, and GLB is always less or equal to the oscillation of f over any interval I containing the point A. So I is the interval which contains the point A. So it means that this oscillation, it is less or equal to oscillation of f over the interval I. Okay, so oscillation of f over the interval I, you have to find this is equal to what's this? This is the least upper bound of f of x where x belongs to I minus GLB of fx where x belongs to I. But since here x is in I, it means that mod of fx minus since or you can apply this, you write this, you name it this star. Okay, you can write this as star. Whenever x is in I, this means fx minus fa less than epsilon. So that means fx, its least upper bound is what? Its least upper bound is fx is less than this fa plus epsilon, and it's also greater than fa minus epsilon. Okay, so from this fx minus fa, mod of fx minus fa less than epsilon means that f of x belongs to the interval fx minus epsilon, fx plus epsilon. So so let's write since by star it's this mod of fx minus f of a is less than epsilon. It's only true when x is in I. So here x is in I, you have to choose you have to apply that star. Okay, you can apply the star as x is in I. So this means that f of x is less than f of a plus epsilon and f of a minus epsilon. So that means the least upper bound, it's like this least upper bound of f of x whenever x is in I, it is it's less or equal to f of a plus epsilon, and greatest lower bound of f of x whenever x is in I, it's greater or equal to this. Okay, greater or equal to f of a minus epsilon. इसका नाम हम डबल स्टार रखेंगे, नेम इट डबल स्टार. Okay, so now look at this this list, it's less or equal to f of a plus epsilon, but this GLB is greater or equal to f of a minus epsilon, then minus times GLB will be less or equal to minus times f of a minus epsilon. So therefore double star gives oscillation of f at a is less or equal to f of a plus epsilon then minus times f of a minus epsilon. Okay, that's equal to twice epsilon. Okay. So this means that oscillation of f at a is less or equal to f where epsilon is any positive number, so which means that oscillation of f at 8 is equal to 0, because this is some fixed number and this is less or equal to every positive number because epsilon is any positive number, and obviously this is independent of epsilon. So that means oscillation of f at a is equal to 0. Now let's prove its converse part. Now we assume that f is not continuous at a. So assume that f is not continuous at a. So by continuity we mean is that for each epsilon positive I can find delta such that whenever for each epsilon positive I can find some interval such that whenever x is in that interval, so mod of fx minus fa less than epsilon. But here it's not continuous, so that means for all epsilon instead we can find, so then therefore there exists for all, instead of for all epsilon positive I should write there exists epsilon naught such that for any bounded open interval j containing a, we have this x belongs to j does not imply does not imply mod of fx. So that means it implies that, does not imply, you can say does not imply that mod of f of x minus f of a is greater than epsilon naught. So this does not imply this. Okay, that means I can find some points. So let's therefore there exists some x naught in G, where G is any open interval. So so whenever this is true for each x. So this is true for each x nested of this. Whenever x is in J, it implies that fx minus fa is greater than epsilon for every x in J. So in particular A is in J. So but A is in J. So not. It's not for each A of x. For each x containing A, we have x in J does not imply this. X is in J implies that this is not less than epsilon. Sorry, this is not less than epsilon actually. Not less than epsilon naught. Not less than epsilon naught. Okay. So we can find epsilon naught such that for any bound open interval J containing A, we have x is in J. We have some x in J. We can write this. Here we can find some point. We can find some x naught is in J. Should write it like this. X naught is in J such that this holds mod of fx minus f of e is less than epsilon naught. Okay, now it's fine. This is f of x naught. Okay, you can find some x naught is in J. So J is any bounded open interval containing A. J is any bounded open interval containing A. You can find some such that this is not less than epsilon, or it does not imply this is less than epsilon. So that is you can say this. F of x naught does not belongs to this interval. Which interval? This f of a plus epsilon naught and f of a minus epsilon naught, f of a minus epsilon naught and f of a plus epsilon naught. So this means that f of x naught is either less than this f of a minus epsilon naught, or f of x naught is either greater than f of a plus epsilon. It's not in this interval. Okay, this is the interval with center at f of a. So this is f of a. So here it's f of a minus epsilon naught. Here it's f of a plus epsilon. So this is the interval. Okay, and f of x naught is not here. So that means that f of x either lie in this part or in this part. So either f of x naught is less than f of a minus epsilon naught, or f of x naught is greater than f of a plus epsilon naught. Okay, so let's take the case 1. Let's take this case. So this is here f of a minus f. Suppose f of x naught lies here. It's in this part. So that means f of x naught is less than f of a minus epsilon naught. Okay, f of a minus epsilon naught. So here it's f of a plus epsilon naught. So this now let's find the oscillation. Now let's find this oscillation of f at the point A, which is the GLB of now let's see this oscillation of f at J, which is equal to the least upper bound of what? F of x, where x runs over j, minus GLB of f of x, where x runs over j. So it means that what does it mean? It means that there is a point x such that f of x naught is less than this. So that means this is not the greatest lower bound. This number f of a minus epsilon naught or f of a plus epsilon naught, they are not greatest lower bounds. They are not greatest lower bounds of f of x over that interval. So, or you can say this f of x naught, what's the GLB? So f of x naught is not here. Okay, f of x naught is not here. Whenever x naught is in J, f of x naught is not here. So this is fact, you can say that x naught is here. Okay, I have x naught is here. So what's the GLB of f of x and what's the least upper bound? So I want this to be greater than some point. Okay, this to be greater because I want contradiction actually. So how do I find that contradiction? So this should be, this epsilon naught should be somewhere here. This should be somewhere here. F of x naught f of x naught so because we have a point, whenever x is in here we have point f of x naught, so that lies outside of this, that's not in this interval. Okay, so that means the GLB, if those points are on this side, okay, or on this side, so whenever those points are on this side, or there is some point on this side also as well, so at that moment what we can do, so if all the points whenever x in J, suppose all the points are on this side, then obviously the GLB is f of a minus epsilon naught, or that GLB is greater than f of a plus epsilon naught, or least upper bound is greater than f of a plus epsilon naught, because by assumption that suppose those points lie on this side, so whenever x naught, whenever the points x naught is in J such that this f of x naught, they don't lie in this interval, so in that case the least upper bound is greater than f of a plus epsilon naught, and the greatest lower bound is obviously less than this number, because these points lie here. So I can say this least upper bound, it's greater than it's greater than f of a plus epsilon naught, this number, because those fx lie on this side, and at the same time the GLB is obviously greater than, okay, GLB is obviously GLB is greater than f of a minus epsilon naught minus times GLB. So least upper bound is greater than here, because f of x does not lie in this interval, so that means this is not the least upper bound. So it's the least upper bound is a number which is maybe greater than this, and GLB is a number. This is not the GLB. So actually this there is a point x naught in J, so that f of x naught is not in the interval here and there. So that means this number is not the least upper bound. So least upper bound must be a number greater than this, okay, and the greatest lower bound is a number must be greater than this number, okay. So this means that here it's we have f of a, okay, f of a. So I can say this is GLB must be least upper must be greater than the greater than this number, and GLB must be less than this. Then minus times GLB must be greater than minus times this number. So it's minus times f of a minus epsilon naught. It's like this. Because you want to find the least upper bound of fx. So this least upper bound can't be less than this, and GLB cannot be greater than this, okay, because if least upper bound less than this and GLB greater than this, then the whole thing lie in this part, which is not the case. Which is not the case, okay. This is not the case. This one. F of a is a point, so obviously this is this is in the interval, so f of a must be greater than, I can say it's so this is GLB, so GLB must be here it's GLB, so here it's here it's LUB, here it's GLB. If it's not GLB, that means, so if it's not GLB, that means there is a number which is strictly less than this. So f of a is obviously less than the GLB. I can say less than, not greater than GLB. So f of a, because a is in the interval G. So actually I want to find least upper bound of fx over the interval G. This is my point. So here it's the images are not in this interval, so that means the least upper bound, they must be greater than, okay, this is greater than f of a plus epsilon naught. This is and the GLB must be less than f of a minus epsilon naught, so that minus times GLB must be less than minus times f of a minus epsilon naught, okay. So that's equal to twice epsilon naught, which is a positive number. So now you apply GLB, because G is in any open interval, bounded open interval containing A. So GLB of oscillation of f over G is greater or equal to twice epsilon naught, which is a positive number. So that means oscillation of f at A is positive. It's some positive number. So whenever f is not continuous at a point at this point here, then oscillation at that point must be positive number. Must be a positive number. So this is very crucial point here. How do we write this? It's greater than, because f of x is not in this interval, okay? It's not in this interval. So it's outside of this interval. So it's not here, okay? This is the interval. This is whenever x in J, this fx is not here, okay? It's not here. It's outside of this. So that means this cannot be least upper bound of fx over this interval, and this cannot be the greatest lower bound of this interval over this interval. And f of a is obviously f of a is somewhere here. This is, so f of a lies in this interval, okay? So f of a is always less than f of x naught plus epsilon. That's always true. This is always true. and this a is in J, it means that f of a must be less than least upper bound of fx, and f of a must be greater than GLB of f of x. Okay, this is true. This thing. Okay. So actually this is actually the vertical line, or the horizontal line. Can think this is the interval J here, and this is it. Okay, so this is it. So that actually there is a jump at this point. Whenever this x and J, this f of x is not in this interval. Okay, it's not in this interval, it's outside of this interval. So that's it. So we have proved that oscillation, if f is continuous at a, then oscillation of f at a must be equal to 0, and if f is not continuous at a, then oscillation at that point must be positive. Must be positive thing. Now we have one more theorem. This is theorem. So that's very simple. This one. Let f be a function from R to R. It's a function from R to R. And let R be a positive number. Okay, it's some positive real number. And let's take this ER. ER is a set of all points A. It's those real numbers such that oscillation of f at A is greater or equal to 1 divided by R. Okay, then this ER is continuous. Then ER is sorry, ER is closed. Then ER is closed. Okay, then ER is a closed subset of R. So we need to show that every limit point of ER must lie in ER. So let's choose any limit point. Let x be a limit point of ER. We show that x belongs to ER. That is, we need to show that by this property for x, oscillation of f at x must be greater or equal to 1 by R. This we have to show. So for this, if we prove the oscillation of f over any interval containing x is greater or equal to 0, then oscillation of f at x must be greater or equal to 1 by R. Greater or equal to 1 by, sorry. If we prove oscillation of f over any interval j containing x is greater or equal to R, then oscillation of f at x is also greater or equal to R, because oscillation of f at x is the GLB of such numbers. So it is suffice to show that oscillation of f at j is greater or equal to 1 by R for any bounded open interval containing x. Okay, so from this we obtain this oscillation of f at x is also greater or equal to R, because oscillation of f at x is the GLB of such numbers. So let's take any open interval. Let J be any bounded open interval. Okay, open interval containing J be any bounded open interval containing containing x. Okay, so that means J is an open interval containing x. Since x is x is a limit point of ER, so that means the intersection of J and ER is non-empty. There must be some intersection point of J and ER. So we can choose some y which belongs to er as well as j. Okay, we can choose some point, we can choose some y which is not equal to x, obviously different from x, in R such that this y is in this intersection. So now now this y, so let's see, j is any boundary open interval. Okay, now since this y, it is in ER, y is in ER, so this means that oscillation of f at y is greater or equal to 1 by r, because y is in ER, because this y, it is in ER. Okay, so at this y, it's but this it's also contained in j. This y is also in j, but y also belongs to j, so therefore oscillation of f at y, which is equal to actually the GLB of the oscillation of f over all the interval is j containing the point y. So this thing is actually greater or equal to oscillation of f at j. Sorry, this is a so this one is greater, so this is not true, this is less or equal to, this is less or equal to, okay, oscillation of f at jy, because this is by definition it is the GLB of the oscillations of f over j, where j runs over all the bounded open intervals containing y, and this j is the bounded open interval containing y. It is one of the intervals. So that means this point this point lies in that set of which this number is GLB. So that means this GLB, it must be less or equal to the every member of the set. Okay, now but this one, you can see this is greater or equal to 1 over r, so this is greater or equal to 1 over r. This is should write here, this is greater or equal to 1 over r, this is greater or equal to 1 over r. So 1 over r is less or equal to oscillation of f over y, which is less or equal to, so that means oscillation of f over j is greater or equal to 1 over r, which means that, but j is any bounded open interval containing x, that means oscillation of f at x is greater or equal to 1 over r, which means that x belongs to ER, and hence ER is a closed set. So hence ER is a closed set, hence ER is a closed set. ER is a closed set. Okay. So this proves the set ER is closed. Now we have a very important theorem. Okay. So this is the theorem. Let f be a function from R to R, and let D be the set of discontinuities of R. वो सारे पॉइंट्स जहाँ पर f डिसकंटिन्यूअस है, then D is of type f sigma. Okay, आपके पास एक एग्जांपल है जो मैंने ऑलरेडी बताई. You have a function from R to R which is continuous at irrationals and discontinuous at rationals, and we know that set of rationals is of type f sigma. It's of type f sigma because it's the countable union of closed set of rationals. Okay, so here in this example the set of discontinuities of f is the set of all rational numbers, and set of all rational numbers is of type f sigma. But here we prove the more general result. If f is a function from R to R and D is the set of discontinuities of R, then D is of type f sigma. So in particular from it follows this is an example. Actually you can take this as an example for this, the set of discontinuities of R is of type F sigma. Okay, so let's prove this result. Set of discontinuities of R is of type F sigma. Prove. So let X belongs to T. Okay, X is a set of discontinuities. Then oscillation of F at X is a positive number. Okay, so if it is a positive number, it is greater or equal to 1 over n for some n. It is greater or equal to, then we can, because this is a positive real number. Okay, this is a positive real number. Okay, so you can we can find, let's go explain. We can find some n belongs to Z plus such that oscillation of F at X is greater than 1 by n or greater or equal to 1. This is one and the same thing. If it is greater than 1 over n, then it's also greater or equal to 1 over n. Because since this oscillation is positive, so it's some fixed positive number 1. Now this number also it's reciprocal. This is also a positive number. So this positive number can be dominated by some natural number. So I can find some natural number n such that oscillation of F at X is less than n. Now let's take the reciprocal of it. It's 1 over oscillation of F at X is greater than 1 over n. So that also means 1 over oscillation of F at X is also greater or equal to 1 over n. So because greater than some number also implies greater or equal to. Okay, this is a big deal. So this thing is greater or equal to 1 over n. It means that 1 over r means X is in ER. Okay, 1 over n means X is in EN. So that means for some n. So that means X belongs to union EN and runs from 1 to infinity. X किसी न किसी EN में होगा. Whenever X is in D, it is in some EN, so that means it is in the union, which means that D is subset of union EN. Actually, we want equality. We need to show that D is of type F sigma. That means D is countable union of closed sets. So here D is contained in the set which is of type F sigma, because this set is of type F sigma. It is a countable union of closed sets. Now we put the reverse inclusion. So now let's take any point X in the union EN n runs from 1 to infinity. It means that X belongs to some EN naught. Okay, for some n naught greater or equal to 1. So but whenever X is in EN naught, it means that oscillation of F at X is greater or equal to 1 over n naught. 1 over n naught is a positive number, so which means that oscillation of F at X is positive. That means F is discontinuous at X. F is not continuous at X. You can say F is not continuous. F is not continuous at X. Okay, so which means that X must be in D, because D is a set of our discontinuities of F. So X is one of the point. So that means this union EN n runs from 1 to infinity. It is in D, and hence we have the equality. D is equal to union EN n runs from 1 to infinity. So therefore D is of type F sigma. Therefore D is of type F sigma. So set of discontinuities of F is of type F sigma. Okay. So now next, actually we want to prove that there is no real valued function which is precisely continuous on rationals and discontinuous on irrationals. Okay. So for this we need to show that set of irrationals is So actually we have to apply the Baire category thing. That's the application of the Baire category theorem. We cannot find a real valued function which is precisely continuous on rationals and discontinuous on irrationals. Okay. So as you know that, so let me recall this. Recall this Q. Sorry, let's write this. R is of type F sigma. Okay, is of second category. Sorry. Is of second category. Okay. So then this should be the countable closed union of let's R not let's recall these things. R is second category, and this Q is first category, then Q complement is a second category. Okay, so this we have seen. Because Q complement cannot be first category, we know the union of two first category species is again a first category. So let's recall these things, and now we state the following theorem. So there is no real valued function. There is no real valued function there is no real valued function f from R to R, okay, which is continuous at each, which is continuous at each rational and discontinuous at each irrational. Okay, proof. Assume on contrary that there is a function f from R to R such that first property f is continuous on Q set of each rational point, and f is discontinuous at each point of Q complement. So we know in the previous theorem, we know that the set of discontinuities of a real valued function from R to R is of type F sigma. So that means therefore Q complement is of type F sigma, which implies that Q complement is union Fn and runs from 1 to infinity, right? Where each Fn is closed, and obviously each Fn is subset of Q complement, and obviously Fn is subset of Q complement for all n greater or equal to 1, because Q complement is the union of Fn's. So each Fn contains only irrational points. This is very important. Huh? Each Fn contains only irrational points. So therefore what's the interior of Fn then? It's obviously the empty set, because if it contains any point interior, then there is some interval around that point which sits inside Fn, but every interval contains both rationals and irrational, which is not the case. So interior of Fn is of empty set for all n greater or equal to 1, for all n greater or equal to 1, which implies that so that means that implies interior of Fn closure is also the empty set, because Fn closure is same as Fn, because Fn's are closed sets. So that means this is true for each n greater or equal to 1, which means that each Fn is nowhere dense, which implies that Fn is nowhere dense for all n greater or equal to 1. So that means Q complement is of first category, space. Is first category space, okay? Is first category space. Q complement is first category space, because Q complement is the union of nowhere dense sets. It is union of Fn's, and Fn's are nowhere dense sets, which is not the case, as already mentioned here. This Q complement is second category, okay? It's not a first category space. So it's a contradiction. Which is a contradiction. It's a contradiction. So as required. तो इसमें आपने ये भी दिखाया था Q complement जो है it's not F sigma, it's not F sigma set, okay? Q is F sigma, but Q complement is not F sigma set. So that proves this theorem, okay? So we are now left with only one lecture on this Baire's category theorem, in which we will show that there does not exist a sequence of characteristic functions of rationals which converges to the continuous function, that we will see in the next lecture. Thank you.